Euclidean distance represents the shortest path between two points in Euclidean space, given a point x and the reference point mu in 2D space. The distance is simply the square root of the inner product of their difference. This is also the length of the line segment between 2 points. Geometrically, the network curves of Euclidean distance are perfect circles centered at the origin. In 3D, the surface establishes a symmetric cone equally steep in every direction, treating all dimensions identically. Here's a generalization of Euclidean distance. The Mahalanobis distance replaces the identity matrix with the inverse covariance matrix. This is a sigma inverse. This simple change allows the distance to account for the scale and the correlation structure of the data. To make this concrete, let's consider a real-world dataset from Wikipedia. We use monthly Wikipedia page view counts in January 2024 for 16 machine learning-related articles, split between desktop and mobile users. Each article is a data point in 2D space. We computed the mean vector, about 25,000 desktop views and 16,000 mobile views on average. The covariance matrix captures both spread along each axis and the strong positive correlation between desktop and mobile views. Applying eigenvalue decomposition to the covariance matrix gives two eigenvalues, approximately 6.98 and 0.28 times 10 to the 8th. The large gap between them shows that the data is highly elongated in one direction. The eigenvectors u1 and u2 define that orientation. NumPy makes this eigenvalue decomposition easy to implement. We pass a covariance matrix to NumPy's eigenvalue decomposition and immediately get the eigenvalues and the eigenvectors. Let's prove why the contours of the squared Mahalanobis distance are ellipses. We start by substituting the eigenvalue decomposition of sigma into the expression for sigma inverse. Inverting the eigenvalue decomposition flips each eigenvalue to its reciprocal. The quadratic formula now becomes a weighted sum of squared projections, one along each eigenvector direction. And there's a result. Setting the squared Mahalanobis distance equal to a constant c gives an ellipse equation with a semi-axis proportional to the square roots of the eigenvalues. The covariance structure is fully encoded in the ellipse shape. Here we plot the unit Mahalanobis ellipse directly in the data space of desktop versus mobile page views. The center is as the mean vector and the axes are aligned to the eigenvectors, scaled by the square roots of the eigenvalues. We can rewrite the Mahalanobis distance as the square root of the sum of squared projections scaled by eigenvalues. This is the equation of an elliptical cone, the natural 3D geometry of the Mahalanobis distance. Here's a full picture side by side. The contour plot on the left shows a tilted elliptical contour in the data space. On the right, the 3D surface establishes an elliptical cone steeper along the direction of low variance, shallower along high variance. Let's apply the Mahalanobis distance to each of the 16 Wikipedia articles. Each row is a point in 2D space, and we want to measure how far it is from the center of the distribution. Plotting the data points alongside the Mahalanobis ellipse reveals the structure clearly. Most articles are well inside the ellipse. The article Machine Learning stands out with a Mahalanobis distance of 2.98, the largest distance in the dataset. The article Algorithm presents a distance of 1.78. It has high desktop views but relatively balanced mobile views, placing it at the boundary of the ellipse. The article Computer Science follows closely with a distance of 1.7, also a popular article that drops outside the blue ellipse of distance 1. Here's a complexity ranking. The article Machine Learning is a clear outlier at the top. As we move down the list, articles settle closer to the mean, with the article data mining having the smallest distance of 0.62, the most typical article in this dataset. Thanks for watching this video. Feel free to reach out